Welcome back to Physics 152 Online. I'm going to return to the single-slit diffraction experiment and do a simple derivation of the intensity of the light across the viewing screen. So remember the basic geometry. Monochromatic light comes in from the left through a slit of width A, and what we see on the screen, a little bit surprisingly, is a series of bright and dark fringes. And it's surprising because it's easy to think that that single slit means that the light is coming from a single source. But in reality, that slit is composed of a certain width, and we can analyze the light coming through it by treating it as if it was coming through many tiny sources all right next to each other. And so we can begin doing that by breaking down the slit into little pieces and then writing down an equation for the light that comes from each of these infinitesimally thin portions of the slit, and adding them all up together. The mathematics will look very similar to what we've seen before in our previous interference and diffraction studies. So here's an expression for the incident wave coming through the slit. It's got the familiar form with amplitude A and then the familiar cosine kx minus omega t term, where x is the distance that the wave travels to get from the slit to the screen. Now, when we divide the slit up into many regions, we'll call each one a width delta z. And so from each one of those little regions, a tiny wave, we can call it a wavelet, is emitted. And so all that we do in order to write down the contribution to the overall wave that's produced by the slit, the little piece of width delta z, we'll call it delta y because it's a portion of the overall wave, and we will take delta z, the width of that region, and divide by a, because the overall amplitude A is now getting divided into each of these regions. So delta Z over A represents the fraction of the overall intensity that is being sent through this tiny region delta Z. And here's a picture that hopefully will make it more clear. You can see that the red region is a tiny piece of the overall slit that has width delta Z, and the coordinate system we'll use is to call the distance Z measured from the bottom of the slit. So that's where that little piece is located. And Z equals 0 is the bottom slit, the bottom edge, and Z equals A is the top edge. So X is the distance that the wave has to travel coming from the region delta Z to get to point P on the screen. And we're going to express X in a way that refers it to the average value of X that would be the distance coming from the middle of the slit to point P. You can see that in this example, the distance X is a little bit less than X bar because this piece delta Z is in the top half of the slit. We'll make the approximation, which is a good one if the slit is far away from the screen, that the angle theta is approximately the same for all regions within the slit. So here's the expression for the piece of wave, the wave that's coming from the piece delta Z. So now what we want to do is write down what that path difference is. We'll call it delta x, and it's actually x bar minus x. From the geometry, we can see that that delta x is z minus a over 2 times sine theta. Z is up here. That's the distance from the top of the bottom part of the slit all the way up to our slice delta z, and then we subtract off half of a, and that gives this vertical distance here, which is the hypotenuse of the small right triangle that's formed. So the path difference is z minus a over 2 times sine of theta. And what we can do then is express x as x bar minus this path difference. And so that's all I've done in the next equation is insert in place of x, x bar minus delta x. Now we can substitute in for delta x, and that just makes the cosine term look a little bit more complicated, but we get kx bar minus this quantity z minus a over 2 times the sine of theta, and then minus omega t. So what comes next? Now what we're going to do is replace delta z with dz and perform an integral all the way across the width of the slit to add up the contributions of all of these tiny regions, each of which is emitting a wave. And this will give us, when we perform the integral, the resulting wave at point P. So the integral is simply, all we do with this equation is we replace delta z with dz and move it to the end where it properly belongs for an integral, and then we integrate from z equals 0 to a. And you'll see what changes as z goes from 0 to a. What changes is the path difference. It's inside this overall cosine term. Okay, so the integral is easy to do because the integral of cosine is a sine, right? And then because we're integrating with respect to z, we have to divide by this term that's k times the sine of theta, and there's a minus sign that comes out in the process of doing that integral as well. So this is the integral that's done, and now all we have to do is evaluate it from z equals 0 to a, and I'll do that on the next slide. So this gives a really complicated looking expression. The first term is what we get when we plug in z equals a. The second term comes from z equals 0, and they're almost identical except for a minus sign and a plus sign that's inside the argument. So what we do now, we have the sign of two arguments, and they're taking the difference between them. So we use that sign addition identity, and this will give us a very simple looking expression. The difference between two signs gives us the sine of half of the difference times the cosine of half of the sum. And so when we subtract the two arguments to get this first term, we end up with a term where the omega t drops out. And then the cosine term at the end has the familiar form of a traveling wave. So simplifying this, the minus sign drops out because the sign of the negative argument, that minus sign comes outside and cancels with the one that's outside already. So we end up with a term where the first term out in front of the cosine only depends on the angle theta, which is location of the position on the screen where we're viewing the pattern. Cosine kx minus omega t, that's the familiar traveling wave. So if we use the definition for k so that we can get this expression in terms of the wavelength, we see that the wave resulting at point P is the amplitude A times the sine of this argument divided by that argument itself. So we end up with an expression that actually looks kind of simple. The entire term out in front of the cosine can be regarded as an amplitude, but it's an amplitude that depends on the angle theta. So what we have is a wave that has an amplitude that depends on where we are on the screen. So for certain values of theta, we'll have an amplitude that has a maximum value, and then for other values, we'll have an amplitude that's equal to 0. And that's exactly what we see on the screen, an alternating series of bright and dark fringes. So let's convert this to an intensity, because that was my goal, finding an expression for the intensity as a function of position on the screen. And you'll remember from our discussion of the double slit that intensity is proportional to the amplitude squared. So when we take that theta-dependent amplitude from the previous slide and square it, here's what we get. Then we can just remember that for a single source alone, the intensity is simply proportional to the amplitude of the single source squared. Then we can divide these two terms out, and we can express I of theta over I0 and get just this term that involves the square of the sine function and then the square of the argument. So the result here is that the intensity as a function of theta is equal to I0 times this bracketed term squared. And in order to simplify the expression a little bit, what a lot of textbooks do, and ours is no exception, is it defines this term pi a over lambda sine theta as beta. And so what we end up with is I equals I0 times the sine of beta over beta quantity squared. And what that looks like on the screen is, just to go back a few slides, is the quantity that we had at the start, right here. So there's a big, broad central peak, and then we see a minimum, and then another maximum, and another minimum, and we see the same kind of behavior on the other side of the center of the pattern as well. And so this intensity function explains how we get peaks, but they're peaks that get smaller and smaller as we go further away from the center. Okay, so what now? This equation helps us to understand something that we've noticed in our classroom demonstrations, and that is the following. If we have a two-slit pattern, there are these alternating bright fringes, bright and dark fringes that are close to the center, but we see that as we move a little further away from the center, they get dimmer and dimmer, and eventually we get to a region where there isn't a fringe. There's a fringe that's actually missing from the pattern. And so this, knowing the single-slit diffraction pattern, helps us to understand why this is. What happens is a point on the screen where we would expect to see one of the double-slit bright fringes happens to fall at the same angle where there's a minimum in the single-slit diffraction intensity pattern. And so when that happens, you get a 0 multiplying a term that's positive, but the 0 kills it out. So we can write down, using what we've just calculated from the single-slit diffraction pattern, we can write down a rather complicated but very comprehensive expression for the intensity from a double-slit pattern. We started off by writing it down, I of theta, as 4 times the intensity from a single source times this cosine squared term. And now what we're going to do, that I1, which is the intensity from a single slit, we're going to replace that with the expression that we had for the intensity of a single slit. So I1 becomes I0 times the sine of this quantity over that argument squared. And so then we end up with the rather complicated function, but we see it's a product of a cosine squared term that oscillates back and forth from 0 to 1, 0 to 1 over and over again, but then it's modulated by this sine squared term, which the sine term goes again from 0 to 1 to 0 to 1 again. And that means that these individual peaks that come from the double slit get smaller and smaller, and eventually they vanish. And that's why in some of these patterns there are missing fringes. So here's an example problem that relates directly to this missing fringe. If a double slit interference pattern is observed with monochromatic light, a slit width of 0.01 millimeters, and a slit spacing, that's the distance between the slits, of 0.2 millimeters, how many interference fringes will be visible inside the central diffraction peak? So we go back to this geometry, and here's the diffraction peak like this, and because it's actually a double slit experiment, there will be lots and lots of closely spaced interference fringes inside that overall central peak. So that's what we're going to try to do, is figure out how many double slit interference fringes there are. How do we attack the problem? First, we use our equations for the location of the minima in the single slit pattern and the maxima in the double slit pattern to find out which interference fringe falls at the first diffraction maximum indicated in the sketch. And that's easy because here's the equation for the first minimum in the diffraction pattern. A sine theta 1 is equal to lambda. That gives us the condition for this angle theta 1. Now we use the expression for the interference fringe maximum. D sine theta is equal to m lambda, where m is an integer. And if we take these two equations and combine them by solving for theta 1, for sine theta 1, and substituting into the other equation, we can solve for m. And that's easy to see what happens. M is d sine theta 1 over lambda from the second equation, and we can replace sine theta 1 as lambda over a, like this. So the lambdas cancel, and we get m equals d divided by a. D is 0.2, a is 0.01, and so we get an answer of 20. It's exactly the integer 20, which means that starting from the center, the 20th double slit interference fringe is missing because it falls right at the location of the first minimum in the diffraction pattern. So what that means is we've got a fringe at the center, which is m equals 0, and then there's 19 more on either side of the center that are visible, and the 20th one is missing. So 1 for the central peak plus 19 gives us 39. So the answer to the question is we will see 39 fringes inside this central diffraction peak, and then the next one on either side will be missing. I hope that's helpful, and we'll talk about this more in class.